Progress.
All right, so generally, what is the concept of material balance equation? This is just a concept that explains the fact that if I have a reservoir that is filled with hydrocarbon and water, we know that generally as you're also producing hydrocarbon and you're producing water. During this production, the pressure of the reservoir is dropping. As the pressure of the reservoir is dropping, the pressure on the fluid is also dropping and the fluid is expanding. So what is happening at the end of the day is that within the reservoir, the same volume that was occupied by whatsoever before the drawdown, that same volume will be occupied by a different quantity. It's not as if the volume is going anywhere. That volume is going to be occupied by something else. So if I am drawing, for example, gas out of a reservoir, the remaining gas that is found inside the reservoir expands and occupy the same shape, the same space that the original amount of gas was expanding, was occupying. So that's a basic idea about material balance. If we are talking about oil reservoir, for example, it means that as you're drawing down oil, we may have an aquifer where water from the aquifer moves into the reservoir and occupy the same amount of space that the oil that has been drawn out of the reservoir was occupying. So that is general concept of material balance equation. So we are going to first start by looking at the material balance equation of gas reservoir. PowerPoint. Okay, so we are going to start by looking at the materials balance equation for a gas reservoir. We are just going to take some cases and just discuss about them because there is no way we can discuss all the various cases that may arise. So the first thing we are going to look at is a volumetric dry gas reservoir. A volumetric reservoir is a reservoir where there is no water influx. That means if gas escapes from the reservoir, there is no water that comes in to replace the gas that has escaped. What will happen is the remaining gas will by themselves expand and occupy the same space that was occupied by the original amount of hydrocarbon. So if you look at if we are talking about the same concept that I explained, then you realize that at the beginning, formation volume factor, I believe we have talked so much about the formation volume factor. This is just talking about the change in the volume of hydrocarbon as you're moving from high pressure zone to low pressure zone. What is happening to it? We know that definitely when pressure is relieved on a material, the material expands. So the formation volume factor is the volume at any reservoir condition divided by the volume at standard condition. A standard condition of 60 degrees Fahrenheit and 14.7 psi. So if I have my initial formation volume factor and I have the amount of hydrocarbon that is in that particular reservoir, all of this now gives us the volume of hydrocarbon in that reservoir. And we are now saying that by the concept of material balance, when you produce some amount of gas, what will be left in the gas now will be the initial gas that was first of all there minus what you have produced. But you have to bear in mind that what is left in that reservoir still occupy the same space that the initial amount of hydrocarbon was occupying, because gas has that tendency to expand out when pressure is released and occupy the container. It occupies the entire container. You might have a small quantity of gas, it occupies an entire container. You still increase quantity of gas, maybe multiply it by 10, and they still occupy that same container. So that's just the idea here. The initial amount of space, the space occupied by the hydrocarbon is the same as the same space occupied by the same hydrocarbon after production must have taken place. So we are saying G here stands for the volume of gas at initial reservoir condition. And then the GP now is the volume of gas produced. So G minus GP now is giving us the volume that is left after the production. This is initial, this is produced, then the difference now gives us what is left. Now, if I rearrange this equation, it will give me this particular equation that I have. If I rearrange this equation that I have here, it will still be the same as this equation that we have. This equation that we have. I don't want to expand the PowerPoint because when I do that, my machine freezes. So I don't want to expand the PowerPoint. Now, what is the formula of formation volume factor? Remember, I have said the formation volume factor is the volume of hydrocarbon at reservoir condition divided by the volume at standard condition. So if I take BGI, which is the initial formation volume factor, I divide it by the final formation volume factor. If I take these two quantities and divide, it is going to give me this particular term that I have here, this particular term. This is what is going to give us. It's going to give us this. So this tells us that BGI all over BG is the same as ZP, Z1P divided by ZPI. PI or P1, PI is just the initial. So if I take this quantity, it is the same as this in terms of gas compressibility and the pressure. In terms of gas compressibility. Gas compressibility is just the deviation of gas from the ideal case. We know that we have two types of gas. We have real gas and we have ideal gas. Ideal gas is gas at standard condition. But you know that when gas now is existing within the reservoir, it is no longer under standard condition. So it will not obey all the pressure laws, the Charles law, and the Boyle's law, and all of that. It is not going to obey all those laws because it is only ideal gas that obey those laws. But definitely when it is at reservoir condition, it will not obey that particular law, which is generally given as PV is equal to nRT. That's the ideal equation. But at reservoir condition, it will not obey that condition. So the compressibility factor is just telling us how the gas at reservoir condition has deviated from the ideal case. How it has deviated from the ideal case. So if they are talking about compressibility factor of, let's say, 0.9, it means that the behavior of the gas is closer to standard condition, is closer to ideal case. But if they are talking of 0.6, it means that they are too far apart. That means the behavior is very far away. All right. Now, if I take this BGI divided by BG, which is this expression, and replace it in this equation, I'm going to have this particular equation where I have GP is equal to G into 1 minus that. All right. Maybe I do a little bit of expansion. Okay, so this is what I'm talking about. So we have this equation. This is our BGI all over BG, which is generally going to give us this. The formula of BGI is there and the formula of BG is there. If you take this divided by this, there are some terms that will cancel out, like temperature. Temperature is going to cancel out. There is a constant there that will cancel out to end up to give this. If I take this equation and replace it back in this formula, I'm going to have this particular equation. Then we have just said where Z is a compressibility factor. I've just taken time out to explain what compressibility factor is, all of that. We can rearrange this particular equation so that we see P all over Z is equal to all of this quantity, is equal to all of this quantity. And if I expand this bracket, I will have P all over Z is equal to Pi all over Zi minus Pi all over Zi G, then GP. So it means that if I take this in the form Y is equal to C plus mx, equation of a straight line, If I draw a graph of P over Z against GP, it's going to give me a straight line. Because if you draw a graph of Y against X, it gives you a straight line. When it gives you a straight line, the gradient of that graph is equal to this quantity that is attached to GP. This quantity that is attached to GP, initial pressure, initial Z factor, we know them. So the only unknown here is our G. Remember that G is the gas that is initially in place. G is the amount of gas that is initially in place. That means if I have a table of values of PZ and GP, I can use this P all over Z as a quantity on the y-axis. I draw it against GP. It gives me a straight line. The gradient of that straight line, which I can use to calculate the value of G using Pi and Zi, which are the initial pressure and the initial Z factor. So what we will do now is we have an example here. We are going to go to Excel and see how we can plot that to obtain the value of the initial gas in place using the material balance equation. All right, so I'll reduce this back. Now, we say at discovery, an initial reservoir pressure of Pi equal 3,600 psi is determined for a volumetric dry gas reservoir. During production, the data shown on the table below were gathered. Using the material balance equation approach for such a reservoir, determine the gas reserve initially in place. So I will go to my Excel. This is our data that we have. Remember, we want to draw a graph of P all over Z against GP. So I'll have my P divided by Z. I'll have this column as my P divided by Z. I'll highlight it and increase the size so that we can see it well. All right, that's our P over Z. P over Z means I take P, which is this. So I'll come to this column. I will put my equal to, because I want to put a formula. I will take P divided by Z. Then that's a value. So I take it down, and the rest of the formulas are then inputted and the calculation is done. So this is my value of P over Z. Remember, I want to draw a graph of P over Z against GP. This is GP, the gas that is produced. So I will go to my chart. I will take, let's take scatter plot. We'll take scatter plot in this case. So I will select my data. I'll just put the MBA for gas. Then for the x-axis, I have my GP. I'll highlight that. Then for the y-axis, I have my P over Z. P over Z. I highlight that. That's all right. That's okay now. So I may now add my axis title. So this axis we have P divided by Z. We could increase the size. And on this axis we have gas produced. All right. So that's our gas of P over Z against the GP. I could just add a trend line. So I'll go to format axis. I just come here, I just click a point, highlight, and then I'll see add trend line. I'll add a trend line there. So that's a straight line. I can format the line. Guys, my machine is freezing. Yeah. I'll add the size of the line. I'll take it as solid lines. The color blue is okay. Take it out, yes, like that, and then, all right, that's okay. So I could highlight again, and then I will take display equation on chart. So the software has given me the equation of this straight line. So I don't even need to go and start stressing myself to calculate the gradient because the software has given me the equation of this line. An easiest way to get this GP is to extend this line onto where it meets the x-axis. Where this line meets the x-axis gives us the initial gas in place. But to extend this graph is pretty difficult. So what we are going to do is instead use the gradient of that particular line to calculate the value of GP. So if I go back to the PowerPoint, so if I have my gradient is Pi all over ZG, is Pi all over ZG. Remember, we don't need to use a negative. Just the fact that the graph is slanting simply tells us that it has a negative gradient. So if I say M is equal to all of these parameters, then if I want to calculate G, G is going to be equal to, so if I go back here, our G now will be equal to, so that our G, which is the initial gas in place, is equal to Pi, that's our Pi, divided by Z, divided by Zi times the gradient. And the gradient here is negative 142.23. So we have 142.23. 142.23. All right. Let's be sure of what we have. So we have AZ, A3, A3. We have A3 divided by C, C3. That's our C3 times the gradient. All right, so that's our initial gas in place. That's our initial gas in place. So this is the material balance method of obtaining the initial gas in place for a gas reservoir. It's very easy for a gas reservoir because we have just gas there. But when we come to an oil reservoir, it doesn't become this easy. For a gas reservoir, we may also have a non-volumetric case. A non-volumetric case is a situation where, as you're removing the gas, part of the volume is occupied by an influx of water from the reservoir, from the aquifer into the reservoir. So it means that apart from the space that is occupied by the remaining gas, we also have water that is coming in. And this water that is coming in, remember that part of it is produced. So it means that if water is getting into the reservoir, then we'll end up having gas and water that is also produced at the end of the day. So this now gives us a little bit more complicated formula than what we had in the first case. All right. Now, if we go now to an oil reservoir, the oil reservoir case is very, very complex. Please, I will just advise, let the formulas not be fighting. Nobody is going to require you to go and memorize these formulas at the end of the day. But the truth is the formulas are very frightening, very long formulas. But at the end of the day, we'll see how we can compress this formula into a linear form that we can now use now to do analysis. Now, if initially we have a reservoir that is made up of oil and gas, and you are producing, remember that in this particular case, we have an influx of water. Originally in that reservoir, there is no water because the aquifer is locked up. The aquifer is locked up. So this point down here signifies our aquifer. There is no production, so aquifer water cannot get into the reservoir. When you reduce the pressure by doing production, you are producing oil and you are producing gas. You realize that as time is going, water gets into the reservoir. As more and more oil is being produced, the space is occupied also by part of water from the aquifer. The gas is expanding and occupying also another space and all of that. The oil pressure is dropping below bubble point, and when it drops below bubble point, another gas also evolved from it. So we have two types of gas that we have in this case. The gas cap that was originally there, this is our gas cap. Then we have gas that is as a result of the oil dropping below its bubble point and releasing its solution gas. So the formula becomes more and more complicated because when the production starts, we have the volume now is going to be, we have our new gas cap that is there. We have gas that has evolved. If we are now dealing in the enhanced oil recovery stage, we may be talking of gas that is injected. We may be talking of water that is injected. Remember, the fact that they have put all of this does not mean that it must happen. If it doesn't happen, it means that these various components are zero. These various components are zero. As a result of the drop in pressure, the rock also expand. The fluid also in the reservoir is also expanding as a result of the drop in pressure. Our water also is getting into the reservoir. So you realize that the starting point may be a little bit easy, but the end point is very, very complex because we have too many things that may happen in an oil reservoir during production. So if we have a situation where there is no water influx, then we will just shut down this particular component and then assume that there is no water that gets into the reservoir. But if water is getting in, what is going to be left now is going to be net water because water is getting in and water is being produced. So at the end of the day, what is left in the reservoir now is the net. So there are so many things that come into the reservoir during production as a result of drawdown. So this is why makes the material balance equation of oil reservoir very, very complex. So we'll just flip through some of these concepts to see how we can calculate the entire volume. Because if you remember, if we look at our concept, we are talking about the volume before is the same as the volume after. So before, we are talking of pore volume occupied by oil initially in place. Then we are talking of pore volume occupied by gas initially in place. Initially, we have just oil and gas. But after the drawdown, we have pore volume occupied by the remaining oil, pore volume occupied by the gas in the gas cap, because there was already a gas cap there. So we have pore volume occupied by the evolved solution gas. I already explained when the oil is dropping below its bubble point. We have the pore volume occupied by the net water influx. The net water influx now is the water in minus water out. It tells you now what is left in the reservoir. We have the change in pore volume due to the corner water expansion, due to water expansion, and pore volume reduction due to rock expansion. So as rock is expanding, it is closing up the pore spaces. We have pore spaces, we have rocks. As the drawdown is taking place, pressure is being relieved. As a result of that, the grains of the rocks now tend to expand. As they are expanding, they help to block the pore spaces. And that is one of the reasons why it pushes the hydrocarbon out of the pore spaces. So we have pore volume occupied by injected gas, if at all there is gas injection. Then we have pore volume occupied by the injected water, if at all we have water flooding activities. Now we are going to look at each of them briefly. We are not going to spend a lot of time on them because I said the final formula is very, very complex. Nobody will expect you to go and memorize that final formula. It's very, very complex. But our essence here is to see how it has been reduced to the linear form and how we can use it to determine the reservoir properties and even to determine the flow regime of the reservoir, if we have a volumetric reservoir or a non-volumetric reservoir. A volumetric reservoir is when there is no water influx, and a non-volumetric reservoir is when we have sufficient water influx into the reservoir. All right. So when we talk of pore volume occupied by the oil initially in place, so we have our volume occupied by oil initially in place is the amount of oil that is existing multiplied by the oil formation volume factor, what we are just going to call the initial oil formation volume factor. So that's the definition of what we have there. Now there's a particular term that is going to come in, which we call M. That means at the beginning, we want to look at the volume of oil that exists, the volume of gas that exists within the reservoir divided by the volume of oil that exists between that reservoir. That gives us a parameter which we are going to call M. That gives us a parameter which we are going to call M, because it may be a little bit complex for us to calculate the gas initially in place. So what we are going to do is to bring in a parameter which they call M, which is defined as the gas initially in place divided by the volume of oil initially in place. All right. So if we take this expression and we make the volume of gas initially in place the subject, it means that this particular term will cross, then we end up having this equation for a gas reservoir. We end up having this equation for gas cap, for a gas cap. So we end up having that equation for a gas cap. So this is the equation for a gas cap, M multiplied by the gas volume initially in place. Now, we want to now look at the volume occupied by the remaining oil after the production, after a certain value of pressure. What is the volume occupied by the remaining oil? Is going to be the amount of remaining oil multiplied by the formation volume factor at that point in time. Multiplied by the formation volume factor at that point in time. And if we want to know the remaining oil, we just take the oil initially in place minus the amount of oil that has been produced, the amount of oil that has been produced. So if we go now to the next concept, we want to look now at the pore volume occupied by gas cap at reservoir pressure. What is going to be, what we are calculating here is the pore volume occupied by the gas cap before production starts. So we are talking about this case. We are talking about the first case. How do we calculate this gas volume here? But now, in this case, we are looking at the pore volume that is occupied by the gas after the pressure must have dropped to a particular value. So that volume now of the gas cap, it gives us this volume that was initially in place divided by the initial. We are talking about the volume initially in place. Remember, please. Remember that this is our volume initially in place, MNBOI. So we take that volume initially in place divided by the initial formation volume factor of gas multiplied by the final formation volume factor of gas. Now, if you want to know the pore volume occupied by the evolved gas solution, the amount of volume that is occupied by the gas after the oil must have dropped below its bubble point. After the oil must have dropped below the bubble point. That's what we are looking at now. That volume of the evolved solution gas is going to be equal to the volume of gas initially in place minus the volume of gas produced minus the volume of gas remaining in solution. Minus the volume of gas remaining in solution. And if you want to calculate the volume of gas remaining in solution, you must bring in another term which we call gas solubility. The amount of gas that is in solution is what we call gas solubility. The amount of gas that will dissolve at one stock tank barrel of oil is the definition of gas solubility. That's when you look at the formula now, you now see RS coming into this formula. You now have to bring in that particular formula if you are looking at the volume of gas remaining in solution. So we want to look at the pore volume occupied by the net water. Remember, the net water is just the water influx minus the water produced. Please, when you want to calculate the water produced or oil produced or whatsoever, we are adding formation volume factor to it because as pressure is dropping, the water or the oil or the gas is shrinking. That's why you have to add this to it. It is this parameter that will tell us exactly what we are having, what we had in the reservoir. This parameter will tell us what we had in the reservoir. We are looking at reservoir condition, not what is at the surface. So if you have a particular quantity at the surface, you need to multiply it by the formation volume factor at reservoir condition for you to be able to know the volume that it was at that reservoir condition. All right. The change in volume due to the initial water and rock expansion. This is the general formula of what we call the compressibility equation. This is the general formula that tells us how the compressibility of rock and fluid changes with changes in pressure. Changes with changes in pressure. A simplified form, this is a simplified form of that particular formula. The simplified form to get the volume change. Our essence here is to get the volume change. So if we move away from that, we want to calculate, maybe they have talked about change in pore volume due to initial water and rock expansion. Then we now talk of cornered water expansion. That's the formula of cornered water expansion. We are now talking cornered water is irreducible water saturation. So we have to also bring in the idea of water compressibility factor to it. We have to bring the water compressibility factor and the change in pressure. This is the formula that is used to calculate that expansion. The cornered water expansion, that's the general formula that is used. So the essence is, once all of these things have been calculated, this one is in case we have injection. We have gas injection and we have water injection. So at the end of the day, if you substitute all those quantity in that formula and you make n the subject, this is what it will give us. Remember, the essence, one of the essence of material balance equation is to calculate the value of n, which is the initial oil in place. So if you take all those equations and you put in the original formula, remember this is our original formula, this is our original equation. We are taking all of those equations and we are replacing all of them here. At the end of the day, you are going to, if you make n the subject, this is what you are going to have at the end of the day. So if there is no water injection, I'm already assuming that there are some quantities that will just disappear naturally. this particular quantity, there's no water injection, this quantity will disappear. If there is no gas injection, this quantity will disappear. If there is no water production, this quantity will disappear. So this is the general formula. This is the general formula of material balance, but it can be simplified if some certain things are neglected or if they don't occur at all. So that's the general formula there. Okay, so that's what we have. So this particular equation now can be rearranged to have this particular equation. You can rearrange it in this particular manner so that it is equal to 1. Each of these components that it has been rearranged to is signifying the influence of some particular quantity or some particular energy source on the reservoir. This particular quantity, let's take for example, so if we have all of it, I've defined what A is. From here, I've defined what A is. So this particular quantity now signifies DDI, which is what? Depletion drive index. Remember the various sources of energy that I gave the other day. So we have gas cap, we have water drive, and we have rock expansion. This depletion drive is as a result of solution gas. As a result, so we are talking of solution gas drive mechanism. So each of these now, so if I'm talking about solution gas DDI, this is the quantity that is coming in to influence the reservoir and gives it that particular energy push. Because what we are going to see week after next, when we get into MBAL software, is that you are able to use production data to come out with the energy source of that reservoir, where the energy is coming from. Is it water drive? Is it gas cap? Is it solution drive? So what the software is using is material balance equation to see the influence of each of these particular components on the general energy. So, and at the end of the day, when you add all of them, it should be able to give us 1. So I put all of these things there because when we get into BAL software, when we look at the energy, you should be able to understand exactly where BAL is taking it from. Because what you are using in that BAL is the material balance equation. That's what you use in the BAL to do that energy drive determination. All right, now, what we want to do now is remember that you might use so many formulas, but each formula has its own constraint. Some of those formulas will work for some particular situations. In other situations, they might not give you accurate results. So what are the basic assumptions that they are giving here? That we have constant temperature, we have a pressure equilibrium. All parts of the reservoir have the same pressure and fluid properties are therefore constant throughout. Of course, that can never be possible. So we are just saying that in most cases, these are the assumptions that you're going to use to make sure that this formula becomes valid. Because if you don't use this assumption, the formula will not be valid. So that particular long formula now can be simplified to this particular formula. This is where our basis will be for today. It can be simplified into this particular form. And this form was given by the Havlena and the Odell. They were the one that came out now and decided on how they can string this equation to a linear form that can easily be manipulated. So if I look at this formula, there are some certain things that I can already be eliminating before I get to other things. If there was no initial gas cap at the beginning, it means that the value of M is 0. Remember, the value of M is the amount of gas at the beginning divided by the amount of oil at the beginning. So if the amount of gas is 0, that means we are talking about undersaturated reservoir, then M is 0. Let me redefine this term again. When we talk of undersaturated reservoir, it is reservoir above the bubble point. That means there is no gas that exists within the reservoir. But when they talk of saturated reservoir, it has now reached this bubble point and gas starts evolving from the oil. So if we are talking of undersaturated reservoir, M is 0. This particular quantity becomes 0. If we are talking of volumetric reservoir, where there is no water influx, this particular quantity also becomes what? 0. So in this particular formula, F is equal to what? The amount of oil, gas, and water that is produced. So the amount of oil, this part in front, takes care of the amount of oil and gas that is produced. And then this other part now takes care of the amount of water that is produced. Then EO is the expansion of oil and its original dissolved gas. So the original gas that was inside solution, what happens to it when pressure drops? It expands. So this particular E0 is taking care of that. Then EG is taking care of expansion of gas cap, and EFW is taking care of the expansion of initial water and the reduction in pore volume. So that particular material balance equation have been simplified to give you this form. Please remember again, I've said you don't need to go and start thinking of how you can memorize that formula. We have gone past that age. Even though in Africa, some of us will complicate it, some lecturers may bring it for you to go and handle, but we have long past that age. They cannot be giving you this particular formula for you to go and be memorizing that formula. Nobody does that. All right. So if we have talked about F, EG, and EO and EG, then what is left now is the formula of EFW that takes care of water and the rock expansion. That takes care of water and rock expansion. That is the formula that takes care of water and rock expansion. Change in P is just the P at initial reservoir condition minus the P at a particular reservoir condition. So this goes back now. We are now simplifying the equation based on what I've already said. If we are talking of volumetric reservoir, there is no water influx. WE is 0. If we are talking of undersaturated reservoir, M is 0. So that particular equation now simplifies itself to give us this particular equation. Of course, we already know what F, E0, and EFW will give us. So if I want to calculate the gas initially in place, I can just make it a subject in this equation and it gives me this. So what I'm going to do now is to see how I can use that relationship to determine the energy drive of the reservoir. So what I will do is I will plot a graph of F all over. I will plot all of this on the y-axis against oil production. And then I will look at the trend in which it is appearing. Then I'll be able to know if there is an influx or if I have finite acting influx. Finite acting means that the pressure wave must have reached the bound effect on the pressure change within the reservoir. Infinite acting means that the pressure disturbance has not yet reached the boundary. So I'll be able to calculate this quantity, and then I plot it all over this, and then I'll be able to know now the energy drive of that particular system. So what I need is I need E0 and I need EFW. I need E0 and EFW to be able to calculate that. So what I will do, I don't want to go to Excel and start coming back here again. So let's just see snipping. I will just screenshot this and carry it to Excel so that I don't stress myself. So I have my Excel here. All right, the first one was for gas reservoir. This now. Oh. Okay, so that's my formula. So how do I determine the energy of that reservoir? I need to calculate EO and I need to calculate EFW. What I have here is the average pressure. I have the formation volume factor BO. I have the amount of oil produced, and I have the amount of water produced. So what I'm going to do now is I'll go there. I need to calculate EO. I need to calculate F, I need to calculate EO, and I need to calculate EFW. So I start with F first. I start with F. What's the formula of F? We have NP times BO This is our BO here. Then we have N, the water produced times the formation volume factor of water. If I just flip back to the, all right, the formation volume factor of water, will consider it as 1. It is in this equation, but there's no product, is it there? We'll consider it as 1. So we'll use it as 1. So our F is, we'll put our equal to, we have N, which is the oil produced, that is 0, multiply by formation volume factor, which is C, plus I'll have my water produced multiply by 1. So it doesn't really change anything that much. All right, so our value of F is 0. No, voila, we drag it down and it calculates the other values of F. The next one now is EO. We calculate our EO. Our EO is just BO minus BO initial. So at this level, there is no EO because there is no change. But at this level, I'm going to take this. Oh, I've not put my equal to, I take this minus. I will have to put this value down because this value has to be constant for the entire calculation. Because if you don't put that value, once you drag it down, you will be taking this one, subtracting it from the previous, which is wrong. The right calculation is you have to subtract it from the one that was there at the beginning. That's where you know the real value minus that. So I'm going to put it as a constant. All right, so I drag it down now. It does a calculation for me. Okay. So the next one now is E, F, comma, W. All right. So that formula is a little bit longer. So let's look at it. So we have equal to, we have BO. This is our BO. Remember, our BO is constant throughout. The BOI is what is the constant one, is the first one that we're using. So we don't want to complicate matter. We'll just use it at the beginning. We'll just put 1.3102. Okay. We open our bracket. Oh, bracket. All right. So we open this other bracket because we want to put all of this in a bracket. So I'll open another bracket. I have CW. That's our compressibility of water. Water compressibility is 1.26 times 10 to the power negative 6. So I will just write it down here. I have to cancel this equation because the software will, let's put everything in place first. So we have our CW. Our CW is equal to, we have, what was the value again? We have 3.62. We have 3.62 E to the power negative 6. So we have E to the power negative 6, negative 0.6. All right, that's the value. Let's pick other things also. We have formation compressibility is 4.95. So I have CF. I have my CF 4.95. I put equal to 4.95. 4.95. Capital E. All right, it's okay. If Excel is accepting that, it's okay. If accepting the small one, it's okay. All right, so that's our formation compressibility. We need also the irreducible water saturation. We have our water saturation, the irreducible water saturation. So we are going to go back there. Our irreducible water saturation is 24%, which is 0.24. All right. So you look at this, you look at the reservoir pressure and look at the bubble point. So that's just to confirm the fact that it is undersaturated because the reservoir pressure is above the bubble point pressure. Just to illustrate, just to explain that as a plus. Then our SWI, which is our irreducible saturation, is 0.24. All right, so we go now and do our calculation. Okay, since the water saturation has not been given, we are going to use the same water saturation for SW and SWI. So we have equal to, let's start our formula back. We have our B. I want to write that down because it will be constant throughout. 3102 times. We open our bracket. We open another bracket again because we want to put all of this up. Then we have our CW, that's CW times SW. We'll use this formula plus CF, that's our CF. We close that first bracket, no, the second bracket, then we take divided by. We want to put all of this also in a bracket. So we open a bracket. Oh, yeah. I wanted to shift this, but let's continue. We open in a bracket. We have 1 minus SWI. Then we close it. Then we close the first bracket. We close the first bracket. Then times. We open the bracket. Here we have change in pressure, which is PI minus PR bar. PI is initial reservoir pressure, so it will be constant for all of them. So we are going to use that value, which is 3685. So we'll write it down, 3685 minus our pressure of the reservoir at that point, which is this one now. And then we close it. There are some other things there. Excess formula, very, very complicated. Okay, let's leave that for now. CW, this is CW, the first one, and it was E19. This is E19. E21, which is our water. I will take that off. Then I will put 0.24. Then E20. That's okay. Let me see the formula will go. Not yet. Divided by, if I come here also, E21. Down there is water saturation 0.24. 0.24. I put that value there. see an issue. So we have this E21. I will take E21 off. E21 is formation compressibility 0.1234. 1, 2, 3, 4, 5. Then we have 495. 495. What's happening again? Let's see. Okay, please, let's take it back afresh. Let me take it back afresh. So I have this formation volume factor 2 times. I open my bracket. Then I open the second bracket. I have CW. CW is 0.362 plus I have CF. I have CW times SW, which is 0.24 plus I have my CF 0.12345 I close this, divided by what I have down is 1 minus SW. 1 minus 0.4 will give us 0.76. So I'll just have divided by 0.76. 0.76. Let me put this in bracket. Okay. Times now. We have our change in pressure, which is PI minus the initial reservoir pressure is 3685. I close it. Any bracket I need to close? No bracket. All right. So it's okay now. So I drag it down and it gives us the value. So what we are going to do now is take F. We have to sum these two things. We solve these two columns. So we have E0 plus EFW. So it's equal to, we have this plus this is 0. So you add everything. That's what we have. Then we go now and calculate. Okay, we already calculated F. All right, so we are good to go. We take our, oh, let's not highlight anything. So we take all right, scatter plot. We take scatter plot. We select our data. We go to the x-axis. We select this quantity. No. Oh, please. Yes, we are supposed to calculate. We are supposed to calculate F divided by all of these. So we have this particular quantity that is lacking. So we have F divided by E0 plus EFW. All right. So it means that we have to take this, our value of F. So we have our equal to, we take the value of F divided by this. It will give us error, no problem, because 0 all over 0 does not exist. but the formula will still work in all the cases. Oh yeah, I made a mistake. I took for this one. So I'll change it in the formula there. It is I. It's I, not H. So I'll put I there. All right. Okay, so that's what we have. So I'll just put my 0 there. Just put my 0 there. So if you look at this value, they are more or less constant. If they are more or less constant, it already just tell you that we may be having a plot. We may be having a plot that looks like this. We're having a plot that looks like this. That's what it's just telling us from there, because the values are more or less constant, because we are supposed to draw all of these against the amount of oil that is produced against NP. So if you look at that, it's more or less constant. So let's see. I'm just trying to cross-check this formula to be sure that everything is in place. There's an error there. Let me see. Okay, A2 minus that. All right. So we take our pressure is A3. I'm looking at the negative because there's not supposed to be negative, but I've gotten the problem. It was supposed to be initial reservoir pressure minus the pressure of the reservoir, not pressure of reservoir minus the initial reservoir pressure, because it should not be negative. So we are supposed to take this. It's supposed to be 3, 6, 8, 5 minus. Then you now take this value here. So you now take this value. So you see now it gives us a positive answer. So we take it down. All right. So everything else have changed here. So you realize that once you modify a formula, everything else changes. Because I'm looking at the formula, you have to be very cautious in science. I'm looking at the formula and I'm seeing plus and I'm seeing an answer of negative. You have to verify how on earth should it be giving us negative. That was what I was verifying. So what we have here as our change in pressure is the initial pressure minus the reservoir pressure, not reservoir minus initial. That's where it gives us a negative, because the initial reservoir pressure is the highest pressure. As you are doing production, it is reducing. So everything else has changed. So let's recalculate. Let's draw our plot and see what we are going to have. Let's draw our plot and see what we are going to have. Scatter plot. Oh, you are not supposed to highlight anything when you are going to take the plot. So we have our scatter plot there that comes empty. I will select my data. In the x-axis, I have F. No, in the x-axis, what I have there is my NP, production, oil production. That's my oil production in the x-axis. Then I go to the y-axis. That's what we have, the y-axis. So you give us a curve like that. So what we are going to do, you realize that the values are very, very close to each other. So it is giving us a horizontal plot, and that horizontal plot is telling us that it is a volumetric reservoir with no water influx. A volumetric reservoir with no water influx. That's what it is telling us based on this. All right. So that's how you have to determine the energy of the reservoir. That's how you determine the energy of the reservoir. We have E this and this. F divided by that, and we have 0.9. I'm just cross-checking our formulas to be sure of what we have done. So we have F3, yes, divided by I3, divided by I3. All right, that's okay. All right, so that's what we have. So how can we also use this information to calculate the initial gas in place? Remember, we have drawn this graph to determine the energy of the reservoir. But how do we use this to calculate the initial gas in place? If I draw a graph of F against E0 plus EFW, I expect it to be a straight line. I expect it to be a straight line. So I will just move this graph. I will highlight it. Go back. Okay, I'll move chart. Yeah, let's move it there. So that the graph is alone somewhere else, so that we are not seeing it again. So we can now plot a graph of what is highlighted here. Plot a graph of, we'll just call it a scatter plot first. We plot a graph of, we select our graph data. On the x-axis, we have E0 plus EFW. This is what we have. Plus, and then the y-axis, we have F on the y-axis. So plot that. It gives us a straight line. We may add our trend line to it. We plot on any point we take, add trend line. It adds the trend line. All right, we may display equation on chart. We display equation on chart. That's the equation. Y equal 1x minus 4e raised to the power negative 0.5. So that's what we have. Solid line. Dash format. Solid there. All right. So that is what we have. So remember, when we are drawing a graph of F against this, it gives us a straight line, and the gradient of that straight line gives us our value of n. So from there now, we can obtain our value of n, which is the gradient. And the gradient in this case is equal to 1. The gradient in this case is equal to 1. So this tells us the amount of gas that we had, the amount of oil that we had initially in place. All right. So what I'll do is I'll check another assignment and see if I can send for you to do, to see how you can understand it better and clarify yourself better. Remember, we have confirmed the fact that this reservoir has no influx, has no water influx to it, into that reservoir. That's how we determine the energy of the reservoir. And then the second thing now is we are trying to see how we can determine the amount of hydrocarbon in place. But our target of this class was to determine the drive mechanism. That's our target. It was to determine the drive mechanism by following all of these formulas that we have, all of the formulas that we have for material balance equation, to following all the formulas that we have for material balance equation. All right. So we'll leave it there for today. If there's any question, you can ask. Any question? All right. So if there's no question, we'll continue from there.